Welcome back. Welcome to week 3. I congratulate you for making to week 3. Today we are going to see the fruit of our labor. We have learnt a lot about interest rate, discount rate, then force of interest, then various relations with various frequencies of compounding, and with all that material we have very good mathematical formulations of those ideas. And this time in today's lecture we will start viewing the implications or applicability of those results into real world problems. So today what we will do first is we will start with the equation of value. In the equation of value we will actually appeal to the same concept that we started in week 1, that is time value of money. Money has a time dimension. So because money has a time dimension, we need to have a principle called focal date, which will enable us to actually collapse the time dimension and bring everything to the same date. Now identifying this focal date is the key principle, and once you identify this focal date, and it doesn't we will show that the focal date is our convenience, and once you identify this you can easily solve problems for unknown payments x. So by the end of this class you will be able to solve problems for unknown payments x given a loan you are paying and those unknown payments x are coming. You will be able to solve, and how we will solve? The toolkit is equation of value, which essentially deals with the present value of money. Now where do you find all these things? That is why the reference mapping is given here, and Broverman section 1.3, Chan and Say section 1.8. After understanding the mystery of these unknown payments x, we will actually take up a real world problem which involves drop payment or partial payment. You are taking a loan, you are paying up a loan with some fixed amount in due course of time. However, at the end some partial payment is remaining. How will you settle that payment? That query we will address in the towards the end of the class, and then we will summarize the class. That is what our today's roadmap is. Let us start with the main thing, that is the equation of value. To set that, the first big idea that you can never forget is you cannot add money at different times, which can be said as money has a time dimension, and we have studied since beginning. That is why we need to determine time value of money. To set the references straight, let us say I have $100 today and $100 next year. I cannot say 100 plus 100 is equal to $200. I cannot say that. For example, 100 rupees in the year 1990 and 100 rupees in the year 2020 cannot be added together. Then how can I understand how much amount I have? So to answer that, what we need to do? We need to bring these two money values to a common time point. So 1990 you bring forward to 2020, or 2020 you take backwards to 1990. Both of them should be brought to the same value, and if you add them at that common point, then only you can actually have a clear cut understanding. So what that common point is called? That common point is nothing but a focal date. So what magical thing should happen at a focal date, and how will we set the equation of value using this golden rule of finance? That is what we explore in the next slide. So now we have focal date fixed. We have understood this is the focal date. Then what should happen at this focal date? Whatever inflows that are going to come and whatever outflows that are going to go out from this particular point should be matched. Okay, so that gives us the equation of value. At the focal date, which is the choice of our convenience, the value of all inflows, sum over value of all inflows, should be equal to sum over value of all outflows. That sets the equation of value. For example, 100 rupees coming this month, 100 rupees coming next month, 100 rupees coming next to that. So month 1, month 2, month 3, every month you are earning 100 rupees. Those are inflows, and you are paying 50 rupees every month. Those are outflows. And therefore, when you match these, the balance that is there in your account and the value of outflows should match the value of inflows. Okay. So, that is the idea of this equation of value. So, the amount in your account can also be considered as outflow, not inflow. So, that should be matched. When we will solve examples, this notion will be very much clear. Now that we have understood equation of value and the importance of the focal date, the natural question that comes to our mind is, does the focal date matter? Let us try to answer this question by taking a simple example. You consider a 1 year timeline. You have considered 1 year timeline, a payment of $100 is due at t equal to 1. Due at t equal to 1. So, this is the status, and now I want to replace this, replace the timeline with basically a single payment of X dollars at t equal to 0.5. So, at the half the duration of this payment, I want to make a single payment. Okay. So, this is typically it is a yearly payment, then this will be a 6 months period. That is the idea that we will use. And now we will have two types of interest rate models. For that, I will choose my interest rate for sake of clarity. I will choose my interest rate to be 10%. Okay. So, there are two kinds of models we have studied. One is compound model, another one is simple interest model. So, we want to contrast these two and see whether the choice of focal date matters or not, right. So, let us first handle this compound interest rate model. What does this compound interest rate model say? If I want to have X, the payment of X, which is the present value at time 0.5, then how will I compute that? It will be 1.10, when is the payment due? 0.5. So, it will be 0.5 equal to say 100. Okay. What I have done? I have actually taken a point which is 6 months ahead. So, this is not actually the present value, but it is the value after 6 months for that $100. So, if I draw a timeline, what I am looking at is, if this is t is equal to 1, I am looking at this value, which this value is x, and this is t is equal to 0.5. So, how will I calculate this? It is very simple. Then x is going to be equal to 100 upon 1.10 raised to 5, and if that is the case, then what should be my x? Do the calculation on your calculator, is going to be 95.35. Okay. Now, what we will do? We will take this time point focal date t to be equal to 0. So, what I need to do is I need to bring all these values to time point 0 and calculate, right. So, this is a calculation with focal date t equal to 1. Now, take the focal date t equal to 0. What will happen? First, I need to bring those 100 to time point 0 and then bring it back forward by time point 5. Okay. So, naturally it will be first the present value that I will calculate will be 100 divided by 1.1, very clear. Okay. And then whatever that present value is, this is where we will call this as PV1, and then if I call PV2, which is this value of x, right. So, x is the value of that particular thing, that I will bring by 1.1 raised to 0.5, okay. So, that is my PV2, okay. And if at t equal to 0, these two values must be equal, correct. So, now I will equate this PV1 into is equal to PV2. So, that gives me 100 upon 1.1 is equal to x upon 1.1 raised to 0.5, correct. But you take this 1.1 on the other side, then what you got, 100 is equal to x upon 1.1, sorry, you take this denominator of 1.1 on the left hand side to the right hand side, you got x into 1.1 raised to 0.5, right. And therefore, my x, therefore, from this I can say my x is actually 100 upon 1.1 raised to 0.5, which is same as this, correct. So, when I ask this question, whether they are same, yes, they are same. What has happened actually is this multiplication factor, right. So, this 1.1 was a multiplication factor which got cancelled, 1.1 raised to 0.5, it got cancelled, and this is a clear cut understanding that under compound interest rate, because the interest rate accumulation function, say a t plus h, is actually a multiplicative accumulation function. It does not matter whether you use t is equal to 0 as a focal date or t is equal to 1 as a focal date. So, in compound interest, under compound interest assumption, the choice of focal date do not matter, that is one thing. Now, let us check the other growth model that we have studied, which is simple interest rate model. As usual, we will start with focal date at t equal to 1. So, when I start at focal date t equal to 1, I have to bring the x amount forward by 0.5 points. So, it will be simply x multiplied by 1 plus that time, which is 0.05. So, 1.05 it is going to be equal to 100, very clear, at t equal to 1. So, therefore, my x will be equal to 100 upon 100 upon 1.05, which is again going to be something like 95.238. Great. Now comes the real task. T is equal to 0. That means what? I have to do that juggling twice. So, I have to bring 100 to t is equal to 0, then I have to bring this fourth to t is equal to 0.5. So, let us do one by one. I will call again that as PV1, okay. So, I am evaluating 100 at 1, I am bringing it back. So, when you are under simple interest rate assumption, it is 1 plus I t, that is the model, right. So, I will use this particular formulation to bring it back. So, what will happen? PV at 1 will be 100 upon, I am putting t is equal to 0. So, by time 1 time full time I am bringing it back. So, it will be 1 plus 0.1 into 1, okay. So, that will give me 100 upon 1.1, 100 upon 1.1, which we have calculated 90.909, okay. Now, you look at PV2, which is at time 0.5, what is it? It is x, and I am bringing back by time point 0.5 based on this formulation. So, this will be 100 upon 1.05, 100 upon 1.05, sorry, it is not 100, it will be the value x, right, because at time 0.5 it is x upon 1.05, and what should it be equal to? It should be equal to this, which is 90.909. Okay. So, what should be the value of x? In this case, the value of x should become 90.909 into 1.05. So, it will be 95.455, and is this x equal to this x? The answer is no, they are not equal, right. So, under simple interest rate assumption, this particular focal date is very important, because how you are bringing this forward and backward definitely matters. So, whenever you are, if you are under compound interest rate assumption, the focal date change does not change your answer. Under simple interest rate assumptions, focal date can change your answer. So, if you understand this properly, then you will never fall prey to the exam traps. So, my answer here is, under compound interest assumption, does the choice of focal date change your answer? No, because finally it is just the accumulation function that is getting multiplied. So, the multiplicative factor will cancel itself off. So, if A is equal to B at time 0, multiplying both sides with that compounding factor, which is our compound interest rate model, will not change the answer. The equality holds for any time k. However, if you are under simple interest rate assumption, as I mentioned here explicitly with example, the focal date does matter. So, while solving the problems, always check whether the compounding model is simple interest rate model or the compound interest rate model. These are called growth models. So, now that I have understood that if I am under the arena of compound interest, the focal date change will not matter. Only thing is, focal date will be my convenience. So, how will I solve those problems? So, first thing is, we have a 3-step strategy to solving any problem that involves cash flows and computing present value or future value of cash flows. So, here what we do, we place everything that is written in the problem, that is every cash flow, we map it to the time. So, we draw a timeline from left to right, and then we will put all the cash flows at respective time points. What next you will do? You will choose the focal date. Particularly while solving the problems, as I mentioned earlier, it is usually the initial time period, that is t is equal to 0, or the date at which we have to make all the payments, that is the time of unknown payment, right. So, you can actually fix any one of them. Once you fix any one of them, then the equation of value will come into play, and what you will do is, you will take individual cash flow, you map it back or forward to the focal date that you have chosen. Okay. Once you have done that, you are setting inflows equal to outflows, that is all. So, what you are doing, I will repeat once again, you are moving all the cash flows at non-zero time. If your focal date is 0, at non-zero time, you move all the cash flows to time t equal to 0, and then equate inflows with outflows. Once you have done that, then it's merely an algebra or calculator work to solve the problem. So, that's all. So, this is our 3-step strategy. Let us use this 3-step strategy to solve one simple problem, where the problem is very simple. You have borrowed $1000 at interest rate 6%. So, this is effective annual interest rate of 6%, and you repay x at t is equal to 2 and 2x at t is equal to 5. You are asked to find what is the value of x. Okay. So, if you look at the figure that is shown on the slide, the one in the blues are inflows, the one in the reds are outflows. So, this is the timeline that we have drawn. 0 at time point 2 we have to pay x, so it is outflow, so it is marked red. At time point 2x, at time point 5 it is 2x, which is marked red. Now, are x and 2x same in value? The answer is no. So, what we will do? We will actually choose the focal date, correct, and then move all the cash flows to that focal date, fine. So, to do that we have to be very precise about focal date. So, let us say for initial exploration you have chosen the focal date to be t is equal to 0. Okay. So, we are dealing with present value of the money. Okay. So, at present how much is the value of $1000? It's $1000, right. Now, you look at the payment x that you have to make, right. This is to be done at time point 2. So, there are 2 time periods in between. So, if I want to map this to time period 2, we have basic understanding of accumulation function where we actually did something. So, if I have 1 unit rate, then I can actually do V, I can say V is equal to 1 plus I. So, this is the at maturity you have one period, and what should be the value? That value is V, and then we derived one thing called V is equal to 1 upon 1 plus I. So, we will use this particular structure with V notation in our mind, right. So, if I want to move this x backwards to time point 0, I need to multiply by 2 time periods, right. I need to reverse this with 2 time periods. So, what will happen? X will be actually multiplied by V squared, correct. So, if I am mapping it backward to time 0, the value will be xv square. Is that what I will equate with 1000? No, I have this 2x also, and this 2x is actually at time period 5. So, what I will do? I will multiply this 2x because there are 5 periods with v raised to 5, okay, and then I will sum over all of them, and this particular sum I will actually equate to the present value of money, okay. So, what I have done? I have used the interest rate which will give me V is equal to 1 plus I, and I have equated, and I got the equation for value, equation of value, which is 1000 equal to x times V square plus 2x times V raised to 5. You can easily see V is 1 upon 1 plus I, and I is 6%. So, it is 1 upon 1.06 this is going to be V. So, you just simply plug in those values, and then you see the magic happening. That means, I have 1000, just arrange x is a common thing, V square plus 2V raised to 5, and then 1 upon 1.06 will give me 1 by V square to be equal to 0.8900 and V raised to 5 to be equal to 0.7473. Verify for yourself on the calculator, and then if you sum over them, you are simply left with 2.3846 times x is equal to $1000, and therefore x is equal to 419.36. Now, if you see this, the compounding we are doing is this is the discounting that we are doing. We are using a compound interest rate model, right, with annual interest of 6%. Perfect. So, now the next question is, will the focal date matter? And I claim that the focal date will not matter. So what if I do the same calculation with focal date equal to phi? Answer will be similar, but let us check whether when I am doing. So move everything to t equal to phi. Let us go to that flow diagram again. Now I have to move this 1000 to t equal to phi, correct? So how will I do that? It's very simple. 1000 into 1 plus I raised to phi. That's all. Simple formula. So that's the value. What will I do with this x? Again I will move this x to t equal to phi, and how many time periods are there? 3, 4 and 5. There are 3 time periods. So I will move x with 3 time periods, okay, and where will I move this 2x? 2x will be 2x only. So what I will do? I will sum over this, I will equate it to this, that's all. So that's what the equation that we have written. 1000 into 1.06 raised to phi equal to x into 1.06, which is 1 plus I cube plus 2x. Again the same thing, we will solve it using calculator, and you get the value to be equal to 419.36, which is the same answer. Focal date is the choice for your convenience whenever you are operating under compound interest regime. Okay. Now we have understood how this focal date operates. Let us now apply this to a real world problem where you are taking a loan, okay, and that loan actually comes like this. You have taken a loan of $1000. You are paying $300 every year until the debit is cleared. But when you are trying to do the last payment, you may have to pay less than 300. However, this problem is not complete because I have not mentioned what is the rate of interest, right? So assume that 300, 300, 300, you have made up 3 payments of 300, and then the 4th payment is somewhat less than 300. Then what will happen? Okay, so how to do that? So that's or how much to do? That can be the questions, and we will answer those questions in the course of time. So let us take this problem and give the necessary information. Okay. So to give the necessary information, what can be the questions or what can be your strategy is, you have to find the number of full payments first. In this case we have figured out that it is 3, but unless the interest rate is given, I cannot say these are 3 payments. Then second, once you have figured out the number of payments, you have to set up the equation of value for that last small piece which you have to do the part payment for. Okay. So with this strategy, let us try to get the full information and try to solve the problem. So I have a loan, interest rate is 10% per annum, payment I am doing 500 at t equal to 1, 500 at t equal to 2. So I have exhausted the principal amount, okay, and the balance is the final payment at t equal to 3 to clear all the debit. Okay. So now what is my focal point? T equal to 3, or focal date will be t equal to 3. So I will bring all the payments, all the inflows and outflows to t equal to 3, correct? So if I borrowed 1000 rupees at time 0, to bring it to t equal to 3, I need to consider debit that will happen from my account at t equal to 3. Okay. So that is 1000 into 1.1 raised to 3, which is very clear. Now what are the payments that you are doing? You are paying $500 at time t equal to 1. At time t equal to 3, the cost of 500 will not be 500, it will be more than that, right? So you will take the other two periods that are there for which this money is carried over, and you will multiply by 1 plus I raised to that particular those number of periods. That means 500 into 1.1 squared. And then one more payment you are doing at t equal to 2, which is carried over for one period. So 500 into 1.1 raised to 1, and the unknown payment that you have to clear is x. So the total payments at t equal to 3 will be sum of all these three quantities, and the debit at t equal to 3 will be 1000 into 1.1 raised to 3. Set the equation of value. Because everything is at t equal to 3, we have collapsed the time dimension. So if you set this, if you equate this number 1000 into 1.1 raised to 3 will turn out to be 1331. This number which is this will turn out to be 605, this number will be 550 plus x. So I got all the things tidy. So 1155 plus 1 minus 1331 will be minus x, which will give me the final answer to be equal to 176. Very easy. So I have understood how to pay the drop payments at t equal to 3. Correct? So now in order to do this, you have actually done, so you have done lot of things. You have actually taken 1.1 to the power 3, 1.1 to the power 2 and 1.1 to the power 1. In previous example, we had 1.06 which was inverted and then taken to some other powers. So doing this on a calculator can become messy, right, where you are actually typing by hand and you may commit mistakes. So a pro tip over here is you have to use calculator and the memory of the calculator. For example, if you are using your calculator and you have to compute this equation, which is x v square plus 2 v raised to 5, then you can effectively use it using the way we are showing here. You use v equal to 1.06 inverse, which can be given by typing 1 by x after typing 1.06. Whatever answer comes, you use the store function that is available in the left panel, store with the number 1. Okay, so it's stored in your first memory. Then you calculate v square by just adjacent to it is a recall function, recall 1, type x square, and then you store it, whatever is the output, you store it in number 2. Okay, recall again 1, use x raised to y function in your calculator, which is at the top, and once you use that function, you multiply the output by 2 and store this output in 3. Then what you will do, you will simply recall 2 and 3 and sum over them. So that can be done by recall 2 plus recall 3, and then whatever answer you get will be your answer. Okay. So this is the calculator tip. You use this memory function very effectively so that you will save time and you will be precise in getting your answers. Okay. So it's in exam FM, it matters to be more accurate. Okay. Now one more question can come. We are dealing with interest rate. What if I will be given a discount rate in the equations? Yes, you can. So we have already juggled it, right? So we have done a lot of things. So we already know whenever a discount rate is given, there is a relation with this discount factor V, which is 1 minus D. So just plug that 1 minus D into your equation and you can easily compute all the present values. Okay. So this is the key. You should memorize the formulas correctly, or you should be able to derive the formulas correctly if you are unable to memorize them, right. So this is the key, and with this you can easily solve any calculation which is related to present value or loan payments. Okay. So So, we are coming to the closure of our lecture. Let us summarize what we have done. First, we have noted that money has time dimensions. So, to add money, I need to bring it to the common point, and when I bring it to the common point, that common point is called focal date, and on that focal date, we will equate all inflows and outflows. Once we have equated these inflows and outflows, we can solve the problem. One disclaimer that this independence of focal date only works with compound interest. So, if the interest methodology or the growth model is compound interest, then only the independence of focal date works. Otherwise, you have to find the focal date, and with simple interest rate model you have to calculate it properly. Okay. Now, if suppose everything works fine, that is it is under compound interest, so focal date will work, and then you are asked a problem, then the 3-step strategy is: first you draw the timeline, put all the payments on respective payments or inflows at the respective places, then pick the focal date. After picking the focal date, bring all inflows and outflows to that date, the value at that date, and then equate, that is find the equation of value. Once you have done that, then you can easily solve the equation of value for unknown payments X. That is what we have done today. So, in particular, we have also seen one real world example where the final cleanup payment to balance the equation can be computed, which is called drop payment. So, what we are going to do next? So, if you look at this particular setup, you have unknown payment right now. What if your time is unknown? In how many years you are going to pay off the loan is unknown. That is a problem that we are trying to solve next. We can find X, but can we find N? What if the unknown is in the exponent? Okay. So, we have done similar thing, right? So, we have actually done that using logarithms. So, we will review that and we will take some real time examples where we will use that more effectively. So, see you in the next class. Thank you for listening to today's class.